Welcome to the episode of Biogeography program. There have been 5 known ice ages in the Earth's history, with the Earth experiencing the Quaternary Ice Age during the present time. Within ice ages, there exist periods of more severe glacial conditions and more temperate referred to as glacial periods and interglacial periods respectively. The Earth is currently in an interglacial period of the Quaternary Ice Age, with the last glacial period of the Quaternary having ended approximately 10,000 years ago with the start of the Holocene epoch. Based on climate proxies, paleoclimatologists study the different climate states originating from glaciation. Objectives of this lesson are to know about ice ages, glacial and interglacials, glacial and interglacial cycles of Pleistocene, extinctions, identifying causes of particular mass extinctions, duration and timing of mass extinctions. Ice ages, glacial and interglacials. An ice age is a long interval of time, millions to tens of millions of years, when global temperatures are relatively cold and large areas of the earth are covered by continental ice sheets and alpine glaciers. Within an ice age are multiple shorter term periods of warmer temperatures when glacials retreat, called interglacials or interglacial cycles, and colder temperatures when glaciers advance, called glacials or glacial cycles. At least 5 major ice ages have occurred throughout Earth's history. The earliest was over 2 billion years ago, and the most recent one began approximately 3 million years ago and continues today. Currently, we are in a warm interglacial that began about 10,000 years ago. The last period of glaciation, which is often informally called the Ice Age, peaked about 20,000 years ago. At that time, the world was on average probably about 10 degrees Fahrenheit, that is 5 degrees Celsius, colder than today, and locally as much as 40 degrees Fahrenheit, that is 22 degrees Celsius, colder. Many factors contribute to climate variations, including changes in ocean and atmosphere circulation patterns, varying concentrations of atmospheric carbon dioxide, and even volcanic eruptions. The following discusses key factors in initiating ice ages and the timing of glacial interglacial cycles. One significant trigger in initiating ice ages is the changing positions of Earth's ever-moving continents, which affect ocean and atmospheric circulation patterns. When plate tectonic movement causes continents to be arranged such that warm water flow from the equator to the poles is blocked or reduced, ice sheets may arise and set another ice age in motion. Today's ice age most likely began when the land bridge between North and South America, Isthmus of Panama, formed and ended the exchange of tropical water between the Atlantic and Pacific Oceans, significantly altering ocean currents. Glacials and interglacials occur in fairly regular repeated cycles. The timing is governed to a large degree by predictable cyclic changes in Earth's orbit, which affect the amount of sunlight reaching different parts of Earth's surface. The 3 orbital variations are changes in Earth's orbit around the Sun, that is eccentricity, shifts in the tilt of Earth's axis, that is obliquity, and third, the wobbling motion of Earth's axis, that is precession. Ice and sediment cores reveal an impressive detailed history of global climate. Cores are collected by driving long hollow tubes as much as 2 miles deep into glacial ice or ocean floor sediments. Ice cores provide annual and even seasonal climate records for up to hundreds of thousands of years, complementing the millions of years of climate records in ocean sediment cores. Within just the past couple of decades, Ice cores recovered from Earth's two existing ice sheets, Greenland and Antarctica, have revealed the most detailed climate records yet. Records show that ice ages typically develop slowly, whereas they end more abruptly. Glacials and interglacials within an ice age display this same trend. On a shorter time scale, global temperatures fluctuate often and rapidly. Various records reveal numerous large, widespread, abrupt climate changes over the past 100,000 years. One of the more recent intriguing findings is the remarkable speed of these changes. Within the incredibly short time span, by geologic standards, of only a few decades or even a few years, global temperatures have fluctuated by as much as 15 degrees Fahrenheit, that is 8 degrees Celsius or more. For example, as Earth was emerging out of the last glacial cycle, the warming trend was interrupted 12,800 years ago when temperatures dropped dramatically in only several decades. A mere 1,300 years later, temperatures locally spiked as much as 20 degrees Fahrenheit, that is 11 degrees Celsius, within just several years. Sudden changes like this occurred at least 24 times during the past 100,000 years. In a relative sense, we are in a time of unusually stable temperatures today. Glacial and interglacial cycles of the Pleistocene. The glacial period that peaked 21,500 years ago was only the most recent of 5 glacial periods in the last 450,000 years. In fact, the Earth system has alternated between glacial and interglacial regimes for more than 2 million years, a period of time known as the Pleistocene. The duration and severity of the glacial periods increased during this period, with a particularly sharp change occurring between 900,000 and 600,000 years ago. Earth is currently within the most recent interglacial period, which started 11,700 years ago and is commonly known as the Holocene epoch. The continental glaciations of the Pleistocene left signatures on the landscape in the form of glacial deposits and landforms. However, the best knowledge of the magnitude and timing of the various glacial and interglacial periods comes from oxygen isotope records in ocean sediments. These records provide both a direct measure of sea level and an indirect measure of global ice volume. Water molecules composed of a lighter isotope of oxygen, 16O, are evaporated more readily than molecules bearing a heavier isotope, 18O. Glacial periods are characterized by high 18O concentrations and represent a net transfer of water, especially with 16O, from the oceans to the ice sheets. Oxygen isotope records indicate that interglacial periods have typically lasted 10,000 to 15,000 years, and maximum glacial periods were of similar length. Most of the past 500,000 years, approximately 80%, have been spent within various intermediate glacial states that were warmer than glacial maxima but cooler than interglacials. During these intermediate times, substantial glaciers occurred over much of Canada and probably covered Scandinavia as well. These intermediate states were not constant, they were characterized by continual millennial scale climate variation. There has been no average or typical state for global climate during Pleistocene and Holocene times. The Earth system has been in continual flux between interglacial and glacial patterns. The cycling of the Earth system, between of the periodicity present in Earth's eccentricity, is an important question in current paleoclimate research. Extinctions. An extinction event, also known as a mass extinction or biotic crisis, is a widespread and rapid decrease in the amount of life on Earth. Such an event is identified by a sharp change in the diversity and abundance of macroscopic life. It occurs when the rate of extinction increases with respect to the rate of speciation. Because the majority of diversity and biomass on Earth is microbial and thus difficult to measure, recorded extinction events affect the easily observed biologically complex component of the biosphere rather than the total diversity and abundance of life. Over 98% of documented species are now extinct, but extinction occurs at an uneven rate. Based on the fossil record, the background rate of extinctions on Earth is about 2 to 5 taxonomic families of marine invertebrates and vertebrates every million years. Marine fossils are mostly used to measure extinction rates because of their superior fossil record and stratigraphic range compared to land organisms. Since life began on Earth, several major mass extinctions have significantly exceeded the background extinction rate. The most recent, the Cretaceous Paleogene extinction event, which occurred approximately 66 million years ago, was a large-scale mass extinction of animal and plant species in a geologically short period of time. In the past 540 million years, there have been 5 major events when over 50% of animal species died. Mass extinctions seem to be a Phanerozoic phenomenon with extinction rates low before large complex organisms arose. Estimates of the number of major mass extinctions in the last 540 million years range from as few as 5 to more than 20. These differences stem from the threshold chosen for describing an extinction event as major and the data chosen to measure past diversity. Major extinction events. In a landmark paper published in 1982, Jack Sepkoski and David M. Rapp identified 5 mass extinctions. They were originally identified as outliers to the general trend of decreasing extinction rates during the Phanerozoic, but as more stringent statistical tests have been applied to the accumulating data, the Big Five cannot be so clearly defined, but rather appear to represent the largest of a relatively smooth continuum of extinction events. Cretaceous Paleogene extinction event. The KT event is now officially called the Cretaceous Paleogene or KPG extinction event in place of Cretaceous Tertiary. About 17% of all families, 50% of all genera and 75% of all species became extinct. In the seas, it reduced the percentage of sessile animals to about 33%. All non-avian dinosaurs became extinct during that time. The boundary event was severe with a significant amount of variability in the rate of extinction between and among different clades. Mammals and birds emerged as dominant land vertebrates in the age of new life. Triassic-Jurassic extinction event. 200 million years at the Triassic-Jurassic transition. About 23% of all families, 48% of all genera, 20% of marine families and 55% of marine genera and 70% to 75% of all species were extinct. Most non-dinosaurian archosaurs, most therapsids and most of the large amphibians were eliminated, leaving dinosaurs with little terrestrial competition. Non-dinosaurian archosaurs continued to dominate aquatic environments, while non-archosaurian diapsids continued to dominate marine environment. The temnospondyle lineage of large amphibians also survived until the Cretaceous in Australia. Permian-Triassic extinction event. 251 million years at the Permian-Triassic transition. Earth's largest extinction killed 57% of all families, 83% of all genera and 90% to 96% of all species, that is 53% of marine families, 84% of marine genera about 96% of all marine species and an estimated 70% of land species including insects. The evidence of plants is less clear, but new taxa became dominant after the extinction. The Great Dying had enormous evolutionary significance. On land, it ended the primacy of mammal-like reptiles. The recovery of vertebrates took 30 millions, but the vacant niches created the opportunity for archosaurs to become ascendant. In the seas, the percentage of animals that were sessile dropped from 67% to 50%. The whole late Permian was a difficult time for at least marine life even before the Great Dying. Late Devonian extinction. At the end of the Frasnian age, in the later parts of the Devonian period, a prolonged series of extinctions eliminated about 19% of all families, 50% of all genera and 70% of all species. This extinction event lasted perhaps as long as 20 million years, and there is evidence for a series of extinction pulses within this period. Ordovician Silurian extinction event. Two events occurred that killed off 27% of all families, 57% of all genera and 60 to 70% of all species. Together, they are ranked by many scientists as the second largest of the 5 major extinctions in Earth's history in terms of percentage of genera that went extinct. Identifying causes of particular mass extinctions. There is still debate about the causes of all mass extinctions. In general, large extinctions may result when a biosphere under long-term stress undergoes a short-term shock. An underlying mechanism appears to be present in the correlation and extinction and origination rates to diversity. High diversity leads to a persistent increase in extinction rate. Low diversity to a persistent increase in origination rate. These presumably ecologically controlled relationships likely amplify small perturbations, that is, asteroid impacts, etc., to produce the global effects observed. A good theory for a particular mass extinction should explain all of the losses, not just focus on a few groups, such as dinosaurs. Explain why particular groups of organisms died out and why others survived. Provide mechanisms which are strong enough to cause a mass extinction but not a total extinction. Be based on events or processes that can be shown to have happened, not just inferred from the extinction. It may be necessary to consider combinations of causes. For example, the marine aspect of the end Cretaceous extinction appears to have been caused by several processes which partially overlap in time and may have had different levels of significance in different parts of the world. Arens and West proposed a press pulse model in which mass extinctions generally require two types of cause: long-term pressure on the ecosystem, that is press, and a sudden catastrophe, that is pulse, toward the end of the period of pressure. Their statistical analysis of marine extinction rates throughout the Phanerozoic suggested that neither long-term pressure alone nor a catastrophe alone was sufficient to cause a significant increase in the extinction rate. Duration and timing of the extinction events. Extinction rates appear to be higher than the background rate for an extended period lasting the last 20 to 25 million years of the Devonian. During this period, about 8 to 10 distinct events can be seen, of which 2 stands out as particularly severe. The Kellwasser event was preceded by a long period of prolonged biodiversity loss. The fossil record of following first 15 million years of the Carboniferous is largely void of terrestrial animal fossils, likely related to losses during the end Devonian Hagenberg event. This period is known as the Romer's Gap. The Kellwasser event. The Kellwasser event is the term given to the extinction pulse that occurred near the Frasnian-Flammenian boundary. most references to the late Devonian extinction are in fact referring to the Kelvasser, which was the first event to be detected based on marine invertebrate record. There may in fact have been two closely spaced events, here as shown by the presence of two distinct anoxic shale layers. The Hagenberg event. The Hagenberg event sits on or just below the Devonian Carboniferous boundary and marks the last spike in the period of extinction. It is marked by an anoxic black shale layer and an overlaying sandstone deposit. Unlike the Kelvasser event, the Hagenberg event affected marine and terrestrial habitats. Sustained global cooling could kill many polar and temperate species and force others to migrate towards the equator, reduce the area available for tropical species, often make the Earth's climate more arid and average, mainly by locking up more of the planet's water in ice and snow. The glaciation cycles of the current ice age are believed to have had only a very mild impact on biodiversity. So, the mere existence of a significant cooling is not sufficient on its own to explain a mass extinction. It has been suggested that global cooling caused or contributed to the Indo-Ordovician, Permian Triassic, late Devonian extinctions and possibly others. Sustained global cooling is distinguished from the temporary climatic effects of flood basalt events or impacts. At the end of the 19th and beginning of the 20th centuries, when scientists first realized that there had been glacial and interglacial ages and that they were somehow associated with the prevalence of disappearance of certain animals, they surmised that the termination of the Pleistocene ice age might be an explanation for the extinctions. Critics object that since there were multiple glacial advances and withdrawals in the evolutionary history of many of the megafauna, it is rather implausible that only after the last glacial would there be such extinctions. However, this criticism is rejected by a recent study indicating that terminal Pleistocene megafaunal community composition may have differed markedly from faunas present during earlier interglacials, particularly with respect to the great abundance and geographic extent of Pleistocene bison at the end of the epoch. This suggests that the survival of megafaunal populations during earlier interglacials is essentially irrelevant to the terminal Pleistocene extinction event because bison were not present in similar abundance during any of the earlier interglacials. Some evidence weighs against climate change as a valid hypothesis as applied to Australia. It has been shown that the prevailing climate at the time of extinction, that is 40,000 to 50,000 BP, was similar to that of today and that the extinct animals were strongly adapted to an arid climate. The evidence indicates that all of the extinctions took place in the same short time period, which was the time when humans entered the landscape. The main mechanism for extinction was probably fire, started by humans, in a then much less fire-adapted landscape. Isotopic evidence shows sudden changes in the diet of surviving species, which could correspond to the stress they experienced before extinction. Evidence in Southeast Asia, in contrast to Europe, Australia and the Americas, suggests that climate change and an increasing sea level were significant factors in the extinction of several herbivorous species. Alterations in vegetation growth and new access routes for early humans and mammals to previously isolated, localized ecosystems were detrimental to select groups of fauna. Thank you.